Hi, everyone, and welcome to another episode of the Data Science Decoded podcast. Today, I am here with Mike, and Nir Kun joined us, unfortunately, but we're going to continue nonetheless with our papers. And today, we have an interesting paper because there are no equations and no math. There was a logical table there, and it wasn't easy for Mike to comprehend a non-mathematical paper. What do you say about that, Mike?
Yeah,
Just reading.
yes. The answer is yes, yes. Then hello, guys. Actually, I missed our podcast. I think we haven't recorded for 3 weeks or so. So I managed to go on vacation in Greece. It was cool.
Amazing.
Now I come back with new forces and new energy, and let's do this paper. And as Daniel said, it was not so easy for me to read this paper. By the way, this paper is quite similar to many papers about LLMs and deep learning, which don't contain almost any formulas. The only formula it contains is about next token prediction, some log likelihood, which is put in every paper in order to show that it is related to deep learning, to machine learning. But anyway, it was not easy. It is not so easy paper. It is quite deep paper, and
Mm-hmm.
I put some effort into understanding it. And let's see how I have managed how I have managed to comprehend it.
Cool. Yeah, so for our listeners, the paper in question is the famous Turing Test paper by Turing, and you can see it. The name of the paper is Computing Machinery and Intelligence, as far as I can tell, and it's published I think it's in a philosophical journal Mind,
Yes.
and the topic is
Theology and
psychology and
philosophy.
philosophy. Yeah.
Yeah.
Um, so the paper is from 1950, so it's 74 years ago. And again, he didn't go into math or anything in this paper. It's more like his ideas about machines and thinking and computing, etc. And he tried to spell it out. And indeed, that was an I won't say difficult read because I understood what he was saying. There wasn't like a lot of jargon or something that usually if you take a philosophy paper, you need to understand their language. So he tried to define concepts if he used them. And what he did, he tries to answer. So let's start going over I think there's like 7 or 8 chapters. The first chapter is the imitation game. And he says here, I'll read. I propose to consider the question, can machines think? This should begin with the definition of the meaning of the terms machine and think. Cool. If you want to answer the question, let's define those. The
Yeah.
definitions might be framed as to reflect so far as possible the normal use of the words, but this attitude is dangerous. Okay. Um, and he says that like what does it mean? Maybe we should do like a poll or a survey to see what people answer, like yes, no, and do statistics and see what most people say. This is dangerous. He wants to do it in a different way. So instead of attempting such a definition of can machines think, he says I should replace the question by another question, which is closely related to it, and it is expressed in relatively unambiguous words, right? So he says, can machines think? It's too ambiguous. What does machine mean? What does think means? Let's replace it with a different question that in his mind is an analogous question.
By the way, a small remark. I think the term machine can be quite easily defined, and Turing does it in the first 2 chapters, in the first 2 sections of his papers. The most difficult part is to define what is to think, And if you ask me, for example, my 11-year-old son comes to me and asks me, Dad, what is to think, define thinking? I'm not sure I can give him a good answer and non and an unambiguous answer. So it is very complicated notion for me
Yeah,
at least.
I understand and I agree. He did define machines in one of the chapters. Um, so he says, let's replace it with a different, let's call it problem, which is called the imitation game. And the original formulation states that it played with three people. A, B, C is the interrogator, and A is a man, B is a woman. Then the interrogator sits in a room, and then he can interact with the male, or B, the woman, with text and ask them questions. And the aim is for him to act like try to pinpoint who's the male and who's the female, right? Better than chance.
Yeah. By
And
the way,
then,
okay.
yeah, and,
Did
he said that maybe some of the strategy of the male or the female is to answer wrong answers in order to confuse them,
Yes.
right? So there's some dynamics here.
Yeah, I just wanted to add some humoristic observation. You can cut it if it is not if it is too much not politically
Hmm.
correct. But I think this mission to distinguish between women, men, and women today is much more difficult than 75 years ago. It is my personal opinion.
That's true. Today there's a spectrum, so then it's like a classification problem, right? If you have two classes, or you have a regression problem.
Yeah. It is a more or less continuous spectrum
Yeah,
because okay, we are not going to dive in
yeah.
this.
That was a small digression. So, anyways, he says we now ask the question: what will happen if a machine takes part of A in this game? Okay, so now instead of a male and a female, there's a person B. A is a machine and C is the interrogator. Now he tries to classify who's whom. And he says these questions replace our original can machine think. Okay, so he says let's not answer the questions can machine think, too problematic for various reasons. Let's answer a different question. If a machine can play this imitation game and fool a person, the interrogator, by convincing him the machine is actual a person.
Yeah, but by the way, it reminds me something which is called in math. There is no math. There is no, there are no formulas in this paper, but
Mm-hmm.
I can't help myself and not thinking about math. So there is a term in math that is called the surrogate objective. If your objective is too complicated or it is very
Mm.
hard to evaluate it, then
Yeah,
there's a family of methods. I don't remember the exact names, but there is a term which is called surrogate objective. So you are in order to optimize your original objective, you are optimizing the surrogate objective, which is much more easier to evaluate or to optimize. And here we see is a very similar pattern. We
hmm,
don't know to answer this question straightforwardly, so we replace this problem by problem which seems to us less ambiguous.
perfect. Makes sense. He says, I'm going to solve let's say, an easier problem.
Yes.
Okay, so in the next chapter, chapter 2, he says critique of the new problem. And he says, okay, maybe you disagree with me. Maybe that's the wrong answer or the wrong game to play. Um, but he now gives reasons why it's a good idea to separate them and use text, because then you don't have the problem of building a machine maybe that is like a person or a woman or a man with skin, etc. It doesn't have to be biological. So that's he writes here some objections or why he thinks it is a good game to play. I'll try to move on. He says it might be urged that when playing the imitation game, the best strategy for the machine may possibly be something other than imitation of the behavior of men. This may be, but I think it's unlikely that there is any great effect of this kind. In any case, there is no intention to investigate here the theory of the game, and it will be assumed that the best strategy is to try to provide answer that would naturally be given by a man. So again, it doesn't go in the direction of maybe the machine is gonna fool us in some way. It tries to mimic a male, and the machine will try to win this game also. Chapter 3, the machines concerned in the game. So now it tries to define machine. He said think we won't talk about, but machines we will define here. Let's see what he says.
But there is an interesting sentence there. It is natural that we should wish to permit every kind of engineering technique to be used in our machines. And I think it is quite important because the techniques which we used to construct machines 75 years ago and now, I think there are quite different techniques, but still they are engineering techniques. And also the question is, should this machine be constructed by, today computers are not constructed by men. Today computers are constructed by other machines. So you have a question. It is not so simple. Then I said that it is simpler to define machine than define thinking. Okay, it is simpler because defining thinking is really very complicated. But still, defining what exactly is machine is not so simple as well. But I think he managed to define it in a quite structured and precise way in what follows.
Yeah, and here it says that we are the more ready to go so in view of the fact that the present interest in thinking machines has been aroused by a particular kind of machine, usually called an electronic computer or digital computer. So by this time, there's already like some kind of a computer that is also discussed later. He called it like the Manchester. So probably it was in Manchester, and it was electronic. So I think his thinking and his paper came out because he interacted with it and he had some ideas.
Yes.
So he says, following this suggestion, we only permit digital computers to take part in our game. He says it might be too drastic, but he says I shall attempt to show that is not so in reality. Okay, so he says it's not drastic to think about computers, and he says that exactly here he's going to define like a universal computing machine, right? He says he's going to show the digital computers. This is chapter 4. The idea behind digital computers may be explained by saying that these machines are intended to carry out any operations which could be done by a human computer. And back in the day, 1950s, they had a human computer. It was usually people that did repetitive work with instructions. They actually were called a computer, and that's why our modern computers are called computers also. So that's why he compares like digital computers to human computers, because back in the day it was actual somebody's profession to be a human computer. And he says there's like a book of rules, and the machine follows the rules, the instructions, like a human can do, and do calculation, etc. And he says there's like a digital computer can usually be regarded as consisting of 3 parts: store, execute unit, and control. In a sense, similar to what we have today. We have like a place to store the information, the disk. We have some kind of a CPU, which is like executive unit, and also it controls it. So That's still today. And the store, he says, store of information. And it reminds us of the paper of Shannon about information. And actually, he talks about capacity here soon. So that also is related. And remember, Shannon's paper is 1 year prior to this paper. So I
Yes.
think
Yes.
he read Shannon's paper when he was writing that.
No, he's not talking here about the information in the
Yeah,
channels.
yeah, of course he doesn't, but still, I think those ideas of Shannon are also might have been affected his thinking, because soon I'll show you why. He talks here about how computers work with writing numbers, how they can combine or add, multiply and add numbers by using a book of rules. And says the information is usually broken up into packets, etc.
By the way, Daniel, I have a question. I have a question for you. It is
Mm-hmm.
interesting for me to know what do you think about it.
Mm-hmm.
As you mentioned, it is written in the paper that the computer is composed of three main parts, which is control, storage, and execution unit.
Mm-hmm.
And they're talking about some electronic computers, digital computers. But what if one of these parts, for example, storage, includes some, not biological inspired parts, but biological parts, some biological
Mm-hmm.
mechanism which is used to let's say to store information. In this case, should we call it a digital computer? Should we call it machine? Or it is just something between the spectrum of humans and
Okay, so there is an answer to that. It's called neuromorphic computing, and it is a research, ongoing research in academia. Also, some companies, for example, like Neuralink of Elon Musk, they do what's called neuromorphic computing because they combine elements of biology and electronics together. And there's different ways to tackle neuromorphic computing via biology. And that if somebody is interested, you can Google neuromorphic computing. I hope it answered the question.
yes.
Cool. So he says here, the idea of a digital computer is an old one. So he mentions Charles Babbage, professor of mathematics from Cambridge in 1828, so more than 100 years prior. And he built an analytical engine that could calculate using only mechanical parts. He says the
Can you
storage was to
imagine?
be purely mechanical.
Can you imagine the first computer was invented almost 200 years ago? 200 years ago. They're thinking about
Yeah,
computer as a relatively modern thing, but it is not that way. It was first invented 200 years ago.
yeah. And look what he says here. The fact that Babbage analytical engine was to be entirely mechanical will help us to rid ourselves of a superstition. Importance is often attached to the fact that modern digital computers are electrical and that the nervous system is also electrical. Since Babbage machine was not electrical, and since all digital computers are in a sense equivalent, we see that the use of electricity cannot be of theoretical importance.
Yes,
That's interesting, and I agree.
yes.
Right? It says like you can in theory, every computer with electricity you can build using mechanical parts.
So it can be it can be electrical, it can be mechanical,
Mhm.
it can be magnetic or quantum, but it can't be biological. If it is if it contains some biological parts, we cannot think about at least straightforwardly as a machine. We can define it as a machine in its full sense.
Yeah, perfect. Next chapter, universality of digital computers. And here, after we defined what's a digital computer, he says, okay, let's talk about the concept of why they're universal. And he says the digital computers described in the last section may be classified amongst the discrete state machines. Okay, so here he defines what is a state machine, and he gives an example of a machine with 3 states and 2 inputs, and it moves between and has outputs depends on the previous state and the input. So in a sense, like Markovian state machine. And just as an example, right? So that's like the closest to math as we get. And he says this example is a typical of a discrete state machine. And he says why it's useful, because given any initial state, you can calculate future states.
By the way, Daniel, it is correct. Also, this assumption is correct also for the modern computers. They have enormous amount of memory. They have enormous amount of compute, but still, it is a finite state discrete machine. You know, it is not Markovian for sure, but it is just gigantic for discrete state, finite state machine.
Yeah,
and any of your computers, yes.
Exactly, and he says that, and then he tries to calculate how many like different states a specific computer, the computer he knows, like Manchester computer, could be in, and he says the logarithm to the base 2 of the number of states is usually called the storage capacity of the machine. Okay, it's like the channel capacity, but instead of channel capacity, we have storage capacity.
Yeah.
You see, and it's similar to what we discussed prior, that if you have a lot of states or degrees of freedom, you do the logarithm to get some kind of measure of capacity. So again, that's where I see the connection. It doesn't mean it's affected his paper. Just maybe back in the day, they were talking about a lot about capacity of stuff.
Yes.
And he says why it shows why it's useful, because you can add capacities of a machine, because you have the capacity of the storage system, the capacity of the execution engine, and then the total capacity of the system is combination. You add them because it's a logarithm scale, so it's useful. What else is important here?
But a very important observation.
Yeah.
That all these machines are fully deterministic.
Mm-hmm.
If you know the past, you know the future. So there is no any randomness in these old computers, and also in our modern computers. Maybe there are some slight randomness due to some numerical inaccuracies. You know, if you are 64 bits computation, you know, and you are doing this computation many machines, there can be some kind of randomness. But if you are talking about some specific computer, it is fully deterministic, finite state discrete.
Yeah, and he says here, that's the part that is relevant. The specific property of digital computers is that they can mimic any discrete state machine. It's described by saying that they are universal machines.
Yes.
Okay, that's why he defined as universal machine, because every finite state machine could describe, every digital computer can describe any or be designed to execute every discrete state machine. Okay. Let's continue to the next chapter. And then he says contrary views on the main question. So now he goes over various rejections that people have to this imitation game with machines. And I'll try to go one by one. First, the theological objection. Thinking is a function of a man's immortal soul. God has given an immortal soul to every man and woman, but not to any other animal or to machines. Hence, no animal or machine can think. Okay, let's not go deep into theology. He also says like it has a lot of problems, etc. And again, he doesn't want to talk about thinking. He wants to talk about, he said that's a difficult questions. Let's do imitation game instead. That's how he answers it.
As for me, by the way, this objections doesn't seem very valid because for me, my knowledge in philosophy is very shallow, if any, but I presume that animals can think, animals can do
He also
some
says it, yeah.
not complicated actions. So animals can think. I'm not sure about machines, but animals, for me, in my opinion, animals can think.
Yeah. Um, he says same in a sense, like he also thinks animals can think. Anyways, number two, second objection, the heads in the said objection. Is like the objection saying, maybe, but let's us hope and believe that they cannot do so. So maybe they can think, but let's us think that or believe they won't think. He also says that's doesn't require refutation. If you don't, if you wanna, stick your hand in the sand, you can do it. There's the mathematical objection, which I found interesting. And he says there are a number of results of mathematical logic which can be used to show that there are limitations to the powers of discrete state machines. The best known of these results is known as Godot's theorem, and actually there's two theorems, and shows that in any sufficiently powerful logical system, statements can be formulated which can neither be proved or disproved within the system, unless possibly the system itself is inconsistent. So if you build a consistent logical framework, there are statements in this logical framework that you cannot prove or disprove. Or you build an inconsistent logical framework. So that's like Godot's theorems. And he says maybe somebody could use them as an objection. What do you think about that, Mike?
I don't think I fully understand
Hmm.
why it constitutes
Okay.
any valid objection. There are such logical systems. Okay, they
So
exist.
he
So
says why? He says that maybe a machine, because of this Gödel's theorem, um, would be asked a question that it cannot answer correctly because of Gödel's theorem, and then it answers something which is incorrect.
so
Maybe.
so
Yeah, and
so
then
so
he says,
yeah.
what's the
Okay.
problem? He says, okay, maybe there are statements that the system will answer incorrectly. So what? That's not a problem. Here it
Uh,
says, if it is rigged up to the give answers to question as in the imitation game, there will be some question to which it will either give a wrong answer or fail to give an answer at all, however much time is allowed for reply. Well, he's saying like maybe it will get stuck and won't be able to answer, but it doesn't see it as a refutation.
but it is okay. We are, as humans, we can think, and there are some questions which don't have wrong and correct answers. There
You're
are. I can.
exactly thinking as him. Look, he says, we too often give wrong answer to questions ourselves to be justified in being very pleased at such evidence of fallibility on the part of the machines. Meaning, we also make some mistakes and we say wrong answers when we think they're right answers.
Yeah, yeah.
Uh, so
It
he
is
says
interesting.
that's not a big problem.
Yeah.
By the way, taking like Gödel's incompleteness theorems uh, and relates to computers actually was used by Penrose, but uh, he has a book, Emperor's New Mind. Actually, I have it somewhere here, and in the book he's saying machines don't have like consciousness, which he doesn't touch in the paper here. Like Penrose tackles that idea with somehow using Gödel's incompleteness theorem. So Penrose
Uh,
was a famous physicist. He's still alive, and he has a few famous books about it. But let's go back to the paper. Number four, another um, uh, let's say counter argument to the his imitation game, the argument from consciousness. And again, we come to this point saying like machines. He quotes some professors. Professor Jefferson, that says that computers don't feel, they don't have emotions, etc., related to consciousness, and then they cannot think. And then he says, if that's true, then how do I know you are thinking? I only know that I think because I have my own emotions and feeling. I don't know if you, Mike, is thinking because I don't have access to your emotions. So he says, in a sense, this line of reasoning brings us to a philosophical view called solipsism, and he talks about it. Here, it's the view that I cannot know anything about anyone else because I don't have access to his conscious life.
Yes.
And he says like this is not really useful because you cannot do anything with it. Just so that's a bad way to go.
By the way, here, if you are talking about senses and stuff like feelings, thoughts, for me, there are two separate notions. The first notion is just thinking of solving problems.
Yeah,
Second notion is creative thinking, and these are two very separate notions. I admit there are some problems for which you need some creative thinking to solve them. In order to create, to write, to compose a sonnet, you need to be creative, and it is very different from solving some very very complicated mathematical problem. For me, it's just two folds of thinking, creative thinking, and solving problem. Maybe I'm wrong, but I feel this way.
actually, this what you said. He lists as an objection, and we'll get to that. And the objection goes also now today we have LLMs that could do singing in a sense, but they still like mimic our data that we
Yeah,
provided, right?
yeah,
So now is it creative thinking? So they talk about what's creative, what's not creative. He says that it's more like our way of thinking about the world that doesn't actually helps us understand things. Um, and here he also adds, before we move to the next argument, he says, I do not wish to give the impression that I think there is no mystery about consciousness. So he says, consciousness is a great question. There is, for instance, something of a paradox connected with any attempt to localize it. Like, where is consciousness? In my brain, this part. But I do not think these mysteries necessarily need to be solved before we can answer the question with which we're concerned in this paper. So he says there's a consciousness is interesting, but it's unrelated to the questions of can machines think. Okay, that's his view.
yeah. You don't need to understand how the human think in order to answer the question whether the machine can think. I think it is these are two different questions. How and whether. It's just two different questions for me.
And there's a
Exactly
next
what you
counter
want to say.
argument, arguments
Yeah,
from various disabilities. These arguments
yeah,
take the form, I grant you that you can make machines do all the things you have mentioned, but you will never be able to make one to do X, right? So all the people that said, oh, let's say 20 years ago, 10 years ago, natural language processing is nice, but you cannot do, I don't know, writing an email in a nice way, and now they write an email, so those objections are nice, but they're not really strong. Uh, let's see what's the next one. He calls it Lady Lovelace's objection. It in it she states, and she talks about the Babbage analytical engine we described previously. The analytical engine has no pretenses to originate anything. It can do whatever we know how to order it to perform. Okay, so
yeah.
it's similar to what we say today. Like LLMs, they cannot do anything original. They only can do whatever they're trained on. So this is an objections that he already addresses. that
Yeah,
those machines can only, you know, do whatever we tell them.
but actually today's LLM do what we told them. But we just managed to tell them, to order them to be able to do many things. We are training it on huge data sets. We are training it, okay, we are training it on the same on the same task, which is next token prediction, but still, then you are training a model on this simple task. Machine learning model can acquire statistical knowledge, statistical and word knowledge, which is very rich and very deep. So, but still, this machine. By the way, it is a very deep question for me. Our LLMs is just very complicated statistical machines, and we excelled in building data sets and developing training methods in order to give them an ability to generalize. And what is to generalize? For me, to generalize is to be able to perform tasks which is not have been trained during the training process, but something which are different. People are asking LLMs tons of questions, and these questions, I don't think that most of them were part of the training sets.
Yeah.
Although the training sets are huge, but still they are not part of. There are many more possible questions than any reasonable size dataset can include. But still, we managed to build so complicated and so sophisticated statistical machines, which have enough memory and enough ability to retrieve from its memory and memory answers to a question which it didn't see, but it knows how to answer it because it has seen similar questions.
Similar, yeah.
And this similarity is the core. It's a core concept in the generalization ability of the LLMs. So it's still this our LLMs are very sophisticated machines, but for me, I can't tell that they can think. They're just very sophisticated. They know relationships between different terms. They know they have an enormous memory and know how to navigate through its memory. But still, if you ask me whether they can think, I tend to give you a negative answer.
My answer, if you think that linear regression can think, then an LLM can think. Easy.
Linear regression with 10 and power 80 parameters.
Yeah, cool. If it can think, so also an LLM can think. So let's go back to the paper. It says the whole question of, thinking or thinking something new. It says the whole question will be considered again in future chapter under the heading of learning machines. Okay, so look, it's 1950, and in the paper there's a chapter about learning machines. So let's try to move there. And there are a few other objections that we gonna talk. This is an interesting one, the argument from extrasensory perception. So he says here that there's strong scientific evidence that there is like precognition, psychokinesis, telepathy, which is interesting because today it's not the case. But it says, unfortunately, the statistical evidence, at least for telepathy, is overwhelming. So back in 1950s, maybe there were some papers that show that telepathy was working, but maybe today with better statistical methods, we've shown that is not the case. But it's interesting that is open.
I guess this proofs of telekinesis and telepathy, I think these proofs are empiric, like the proofs we are doing today for our deep neural nets.
Okay, so chapter 7, I think it's the last chapter or maybe one before the last. And he says,
this is an interesting question, by the way. Reader will have anticipated that I have no very convincing arguments of a positive nature to support my views. You don't see claims like that in modern papers, very unusual.
Yeah, again, back in the day, there was some humility, like
Yeah.
this thing I know, or that's my views, and here I'm not sure, so
Yeah.
take it with a grain of salt.
People allow themselves to be and to claim that they are not sure. Today it is not the case for the most of the papers.
Okay, let's see how he defines learning machines. Uh, let's see here. He says, as I've explained, the problem is mainly one of programming. Advances in engineering have to be made too, but it seems unlikely that this will not be adequate for the requirements. And then he starts to estimate like the storage capacity of the brain and then of Britannica Encyclopedia. And
Here he's talking about estimate, the previous sentence, estimate about the sizes of go up. Yes,
yeah,
estimate the storage capacity of the brain vary from 10 to power 10 to 10 to power 15 binary digits. And
I think it's more today.
yeah, I think
Because
it
each
is.
neuron you can break more, so there's more degrees of freedom per neuron, so you get even more
Yeah, yeah, yeah.
like, but I don't think that is the like his main core. What's interesting here, he says like a prediction. I try to find it when he says like by the end of the century, which was 24 years ago, he think
Are you
that
sure it is
machines,
here? I think it is in the beginning of this paper, but I'm not sure.
yeah, but he says like machines will be able to play and the imitation game really well, meaning they could fool the observer or the what's the name, the person that in room number C. Let's see what he says here. Here, so that about working. No, let's see. In the process of trying to imitate an adult human mind, we're bound to think a good ideal about the process which has brought it to the state that it is in. So again, he's trying to get parallels from like we humans develop and learn.
Yes.
And we notice three components: the initial state of the mind, say at birth, the education, which has been subjected, the child, and other experience, not to be described as education, to which it has been subjected. And then he defines like a child machine that learns. There's a teacher that is teaching him some things, and then there's the structure of the child machine. It's the hereditary material, like when it's born, what he got. Then the changes that the data he gets, it's like mutation. And natural selection is the judgment of the experimenter. So it's trying to do an analogies between like biology and how we're going to train a machine, which is in a sense far from what we do today. We have like back propagation and calculating the errors and back propagating them, but there are some similarities in his way of thinking, of trying to teach a computer something, assuming we have data. And again, this is 1950. There was no machine learning yet, nothing. So in this sense, it's interesting that his mind went there. He says, I have done some experiments with one such child machine and succeeded in teaching it a few things, but the teaching method was too unorthodox for the experiment to be considered really successful.
Yeah.
The use of punishment and rewards. Okay, so again, similar to
Reinforcement learning.
yeah, but also if you do supervised learning, you penalize with the
Yes.
and then back propagate the error. So
Yes.
similar ideas. Uh, let's see if there's another chapter. No, so I wanna finish with some few words from the last paragraph. Um, we may hope that machines will eventually compete with men in all purely intellectual fields, but which are the best ones to start with? Even this is a difficult decision. Many people think that a very abstract activity like the playing of chess would be best. So even back then, people were talking about computers playing chess. It can also be maintained that it is the best to provide the machine with the best sense organs that money can buy, and then teach it to understand and speak English. This process could follow the normal teaching of a child. Things will be pointed out and named. Again, I do not know what the right answer is, but I think both approaches should be tried. We can only see a short distance ahead, but we can see plenty there that needs to be done.
Really interesting paper, and actually had some thoughts about which is called artificial general intelligence, and are they actually in the correct and the right path towards it?
Mm-hmm.
I'm not sure. I'm not sure these huge statistical models of tens of hundreds of billions parameters is a good and shortest path to AGA. By the way, Jan LeCun is talking a lot about it, and I think he has several papers which try to propose a bit
Mm-hmm.
different approach to train our models. But still, the question remains. By the way, it is a very interesting question. Uh, do our LLMs, the most sophisticated LLMs, which we are talking to it on a regular basis, by the way, I can admit that I use the LLM extensively to understand these papers and to understand these arguments, and I've got some good and very
Mm-hmm.
clear and very elaborated explanation of LLMs, but I'm pretty sure that these LLMs were trained, and this paper and this paper maybe was part of this training set. So I
Yeah.
don't know. I can't answer
No,
this.
so I'll answer it as Turing would answer. He would say, like, LLMs, do they think? I don't know. It's a difficult question, but can they play the imitation game? And
Yeah,
today, ChatGPT 3 and above, they win the game. Meaning, if there is a chat, you don't know if it's a person on the other side or an LLM, and you interact with it. Can you guess which one which better than chance?
I can guess it, and I can do it quite easily. I can ask it very difficult questions on different topics, and then I will use another LLM to check the quality of the answers of on this question, and then, as my assumption is that there is no person which can comprehend, which can understand unrelated topics, for example, biology and math and chemistry and genetics. There is no person who understands, who is
Okay, so
capable.
they're too good, or let's
Yeah,
say they're too
it's not
knowledgeable, and
impossible.
then you
Yeah,
can tell that they're too knowledgeable.
yes, yes,
But
yes.
if
I'm not sure. Well,
we tell them at this like at the system prompt, okay, you are now doing the imitation game. Try to answer like a person would answer.
it is
And
interesting.
then I'm taking this and giving it to you, and you interact with this LLM with my system prompt added. Then it will make it stupid as us, answering in with like some slang, or saying, "What the hell are you talking about? I have no idea what quantum superposition is." Or whatever you're gonna ask them, and then how would you know if it's somebody from the street or an LLM?
Yeah, I think it is possible to know, maybe. And my assumption is that modern LLMs are trained to follow instruction, whatever it is. They have instruction fine tuning and instruction training, And we are doing pre-training of our LLMs on very huge data sets, and then they are doing extensive instruction tuning on the human data sets and RLHF with the reinforcement
Okay.
learning, all this stuff. So
Yeah.
we teach our LLMs to follow extraction in the most exact way, instruction from us. I think regular people don't behave this way. Okay, they don't. They grown up and they were not educated. They're not taught to follow instructions like we do for LMs. So I think if maybe if you are not doing some instruction fine tuning for LMs, when then it is possible for it to pass a Turing test.
But
Maybe.
that's what he says. You it, like it doesn't matter how you tune it as long as it
Yeah.
passes the test or passes the game. And
Yes.
you're in the room, you don't know if you're interacting with a person or a machine.
By the way, it can be quite interesting topic for the paper. For example, you can get some human evaluators,
Yeah, I
and
think they did it, and I think it passes the test. Yeah. Yeah, yeah,
really,
yeah,
I'm
yeah.
tuned,
They did
I'm,
it.
I'm tuned or fine tuned with the instruction tuning.
I don't remember how they did, but already like a year ago, I saw papers that claim that LLMs pass the Turing test.
Okay.
Which again, the test is a mimicking test. It means that they can mimic our behavior and how we answer questions, right? It doesn't
Yeah.
mean that they can think whatever thing means.
Yeah, and this is very important because we are optimizing a surrogate objective. We are not optimizing a real objective because we don't understand what is
Exactly.
the real objective. So you know, it passes Turing test, but whether it is think there is no clear question.
Yeah. Cool. So that was an interesting paper, seminal paper. He said like it's gonna take 50 years to pass the Turing test, and
Yeah.
it took 70 something. So that's cool. He talked about machine learning again, back before there was no such a thing. So he had some good intuition about a lot of things. Um,
You
and
know,
like,
you know. By the way,
yeah,
back in 50s, I think this his prediction was quite accurate because think about what they got in the 50s, which computer they got in the 50s,
yeah,
which size of memory,
yeah,
which
nothing. There was barely
yeah,
anything.
they got nothing, and
Yeah,
still it's assumed that in 50 years there will be human-like computers or computers which can kind of think. So in 70 years and 50 years, for me, it is
amazing.
very,
Yeah,
yeah, it is very very very, very accurate prediction.
yeah. That's my point totally. And I do promise you, Mike, that next week we'll have some math. So don't worry. You want at least in the near future there'll be no more philosophical papers.
No, it was okay. Actually,
Ah,
actually, I
oh,
enjoyed it. I
ah,
enjoyed it.
cool.
I admit that I wasn't able to understand in depth as I used to understand
Mm,
our more mathematical paper. There are some claims which I struggle to understand and which I used LLMs, and still
mhm.
I didn't get an impression that I really understand it in depth. But I think it is challenging, and if the paper is seminal and is a bit philosophical with our formulas, we can do it, but in 3 weeks.
There are some like on the border, like Minsky, which is like one of the fathers of AI in the 60s. Yeah, so 10 years plus after this paper, he has some papers that have some math and but mostly like philosophical. So maybe in the future we'll touch them.
Okay.
Um, cool. So have a great week, Mike. Also to our listeners, and we'll be back on the next episode.
Bye bye.
Bye.